x1 given y1. Suppose I call this value to be, there's a number between 0 and 1, right? Because since x1 is binary, entropy of x1 is at most 1. Conditionally can reduce, only reduce entropy. So this is a number between 0 and 1. Any number between 0 and 1 I can express as the binary entropy function of some value. And similarly, let me equal to the binary entropy function. Suppose you have this thing. Okay, so define essentially P1 and P2 through this relationship. Then, if you look at the entropy of x1 plus x2 given y1, y2, is at least as big as the binary entropy function of P1 convolved with P2. P1 convolved P2 is the following: is P1 times 1 minus P2, 1 minus P1 plus P2. This object. So this is Gerber's law. Right. I'm not sure if I should prove this. Probably not. Okay. So I mean, it's not exactly difficult to do. It's an exercise in the book of Elge Malinkin. The name Mrs. Gerber. There's a story behind this. The lemma is in fact due to Weiner and Ziv. Now, the story is, of course, that Jacob Ziv used to visit Bell Labs very often, essentially every year, and he used to work with Aaron Weiner. So every time Jacob came, there was, of course, a logistic arrangement that we made to where is he going to stay. Around Bell Labs, there are all these elderly widows, or not elderly widows, who rent rooms of their apartments or their houses to visiting Bell Labs types, because the visiting Bell Labs types are typically nice and quiet people. They don't make messes, etc. So we want to have such people as the renters. And when Jacob was there for one summer, working on this problem of the Weiner Ziv problem, in fact, as we know. In the meantime, they were trying to find a place for Jacob to rent, and they were trying to call Mrs. Gerber, who was never home. She was never home, so you leave telephone messages. She would call back, and Jacob and Aaron, they would be having lunch or something. Okay, so no way to communicate. Okay. And then one day, I mean, or a few days later, they just put this particular lemma. The telephone rings. It is Mrs. Gerber's. She says, "I have a room for you." And so, for this, they named the lemma to be Mrs. Gerber's lemma. The paper that is published does not contain any mention of Mrs. Gerber. They wanted to name it like that, but I guess Toby Berger was the editor at that time. He objected to having such frivolous namings of lemmas on this basis, so they had to change the name on the inequality of some binary blah blah blah. But okay, so this is the lemma. It's not difficult to prove, but it is what it is. Now, with this lemma at hand, so with the lemma in our hands, what we have is the following. If IW is this particular number, and if IW happens to be equal to 1 minus H2 of P for sub T, then IW H2 minus is less than 1 minus H2 of P cross P. Consequently, it's IW minus IW minus, which is what we wanted to get there, is bigger than H2 of P minus H2 of P cross P. Now if you plot this one, if you plot H2 of P as you change P from 0 to half, it's enough to do it because the remaining part, half to 1, is going to retrace it back. You end up with exactly this lower curve. Whatever value this is. The max is not at P is equal to a half. Max is
probably the other way around.
Sorry?
HP star P minus H.
Different. You're absolutely right. Thank you very much. I could plot this using a computer, but okay, just believe me, that's a positive thing. Okay. So everything here is above that. Indeed, if you take a look at what happens to the W being a BEC, BSC, you get exactly back this lower curve. So BSCs indeed achieve the lower bound. And you can also prove by a simple argument that the top curve is achieved, the maximum you can get. Or this is the BEC. Okay. But if you don't need that, we need this is sufficient for us. So this is the So the pairs IW and the difference between the IW plus and IW minus divided by 2 has to live above this particular curve. So this says the following thing. So this says that the one of this is the following. This is to say, I can put the following thing from here. If there is some function, call this, let's say, kappa of delta, such that if I of W is between delta and 1 minus delta, if you know that your IW is W is mediocre, but you are not close to the extremes, then and K of delta is strictly positive whenever delta is strictly positive. And the thing is that this K does not depend on the W itself. This is a universal function K, right? It does not depend on what W that you have. As long as your W, your channel is such that not BAC, not BEC, any binary input channel, as long as this channel has mediocre mutual information, then its children, this W plus and W minus, are going to be different than each other. Okay. So this K is the smaller of the two heights here. This is delta, is 1 minus delta. If you look at the height of this function at these 2 points, okay, you get what it is. All right, good. All right, so let's say, so this, let me call this property to be the positive progress property. So we have 3 properties of this polarization transformation. The transformation preserves the mutual information. It creates inequality, and it creates positive inequality unless you are done. Okay? Unless you are completely polarized, you create positive inequality. It's a progress towards the extremes happens. Okay. So Now what? I want to use this one to show that indeed correlation does happen. I want to prove to you that this thing that we saw in the computer is not just some fluke. Okay? It is not some numerical error. It is not some my wishful thinking, etc. It's not a property of the BEC. It's in fact generally the correlation does need to happen. Okay. First note one completely trivial fact. It's the following. If you take a look at the, if you have two numbers, A and B, and if I take a look at this average of their squares, and if you compare this thing to the square of the average. This is bigger, my Jensen's inequality, if you wish. All right. And if I have the equality, if I added here the if I added this one, plus 2ab and minus 2 cancel, okay. You get what you get. So it is bigger than this particular guy here. Okay. Let me get this thing out of the way, because we'll use it. That is the reason why I define this this kappa, this k to be this half the difference. Okay. A and the B, I'll plug in the IW plus and IW minus for the A and D. That's the reason for having that. Okay. Now, I'll draw this picture again, which is over there. So from this W, I created these channels. So on and so forth. So I will compute the following things. On each column, I'm going to compute a few statistics. The first statistic I'm going to compute is the average mutual information. I'm going to be used. I'm going to take a look at the IW, and then this is IW. The mu1 here, I'm going to compute I of these two things, take their average. Mu2 is going to be the sum of the mutual information of all these things divided by 4. So forth. In general, the mu(n) is the following. At the nth column, this is column number 0, column number 1, column number 2. At the nth column, I have 2 to the n sub-channels. Okay. I'm going to simply sum all the mutual informations that this S is going over all plus minus sequence of length. Now, this mu is a very boring quantity because it's always the same. Okay? This conservation of this mutual information says that this number is equal to this number, similarly this number is equal to this number, etc. Okay? So nothing is changing, all the mu's are the same. Okay? So this is just all these mu's are in fact nothing is happening there. for every n. The second statistic I'm going to compute is the, let's call it the mu. I'm going to take a look at the average of the squares of these arms. This would be looking at it here. Mu n is n, same sum. Like that. Okay. Now, look the following thing. Take a look at this new one. It is a squared plus b squared divided by 2. IW itself is a plus b divided by 2 because of the conservation of the dimensional information. IW itself is simply the average of the a and the b. So this is exactly this quantity. This is IW. This is exactly this is mu 0, this is mu 1. Now, if we take a look at the terms which are appearing in the mu 2, now term by term, we'll have here, for example, if you take a look at the mu n plus 1, I can write the following way. I have the sum to the n plus 1 things. Let me write it in the following way and take a look at the s. Instead of doing n plus 1, let me put here n, and then take a look at the IW s plus